Next, we deal with the third most important subsection of this presentation. It's about K-Way Spectral Clustering Algorithm and its usage in wireless sensor network domain. This particular algorithm is a very recent algorithm that has been proposed this year in 2013, and we'll be implementing this algorithm and simulating its results and comparing them with other existing algorithms to find out which one is much more efficient. The main motivation behind this has been described as follows. What are wireless sensor networks? Wireless sensor networks are composed of large number of sensor nodes that are randomly distributed in a region of interest. These nodes are responsible for the supervision of a physical phenomenon and periodically transmitting the results to the sink. As energy saving results in extending the lifetime of a network, this presents a great challenge to existing wireless sensor networks. And to deal with this kind of a challenge, a hierarchical clustering algorithm called as a K-Way Spectral Clustering Algorithm has been proposed in wireless sensor network domain. This algorithm is based on spectral classification. That is, it also considers the residual energy as well as some properties of network nodes. Thus, the approach here mainly seeks to form an ideal distribution of sensor networks or clusters and proposes new features to elect the most appropriate cluster heads. In terms of extending the network lifetime and minimizing the energy consumption, the simulation results show that there has been an improved performance in the networks because of employment of this particular algorithm as compared to existing clustering methods. Let's now talk about the spectral clustering scheme of this overall algorithm. The very first stage includes pre-processing, where the existing wireless sensor network with its base station is converted to a graph structure, and we find various matrices of the similarity matrix, the degree matrix, and the Laplacian matrix from it. In the next stage of the spectral mapping, some of the eigenvectors of the Laplacian matrix are computed, and each sensor node I is then mapped to a tuple representing the values of component I in the mentioned eigenvectors. The next step includes to construct a new matrix U from these mentioned eigenvectors, and the very third stage of post-processing, we use this matrix U and we cluster it using a grouping algorithm such as k-means, and finally we get a cluster. That is, the four clusters in this diagram has been described as from the initial wireless sensor network domain, we get the following clusters. Effectively, two matrices has been used to evaluate and analyze and compare the performances of these protocols. These two evaluation metrics are as follows: network lifetime and energy consumption. Network lifetime can be defined as the time elapsed until the final or the first node in the network depletes its energy or dies. First node dies, or the FND matrix, has been widely used in this entire presentation. Energy consumption. We know that uniform energy consumption is very important for network load balancing. More uniform energy consumption is there's a less possibility for the node suffering a premature death. And if there is a less energy consumption per round, we have much more network performance enabled. Let's now talk about the various simulations that have been employed in this course project. MATLAB software has been used effectively to simulate and analyze this particular algorithm. Besides, we consider the radio energy dissipation model that has been shown in the figure below, and the various parameters that are used in simulations have been shown in the table formulated next to it. As you can see, in the radio dissipation energy model, what it does in general is to transmit L bits of messages between two nodes separated by a distance t, where we have various factors where the energy of the transmission can be determined, or the spent energy can be determined from three important factors dealing with. First one is the E electric, that is the energy consumption per bit in transmitter and receiver circuitry. EFS deals with the free space model's amplifiers energy consumption, and EMS is the multiple attenuation model's amplifier energy consumption. Use all this and the thresholds value D0 to determine what is the absolute residual energy that has been used in this entire process. The other parameters that will be used in the simulation, such as initial energy, area of the network, sink coordination, message size, and the number of nodes, has been tabulated in this simulation graph. Some of the assumptions that have been basically used in the simulations is that supposing a node that runs out of energy, it is considered as dead and it cannot transmit or receive a data. For these simulations, the energy of a node decreases each time it sends, receives, or aggregates data according to the model ratio parameters. Also, we ignore the effect caused by the signal collision and the interferences in the wireless channel. Let's now study the results and observe what we can from these simulations. First one describes the distribution of a wireless network sensor network with the number of nodes being 500 that have been randomly distributed in an area of 200 meters cross 200 meters. The base station is located far away from the sensing area at the particular approximations. The next figure shows the simulation of the leech clustering algorithm, which is centralized with a number of nodes being the same 500. The main problem with leech centralized and DECSA protocols is that the random selection of the cluster heads, as all the cluster heads can be located in a small region of the network that has been shown in the critical area, hence some ordinary nodes would be out of reach. Also, the SNOC algorithm produces 2 to the power n clusters, where n is the number of iterations. It cannot partition the network into any number of desired number of clusters. These are the disadvantages of the existing LECH, C, DECSA, and SCNOC algorithms. Next, we implement a simulation for this particular algorithm of KSCA-WSN. Here we can see that clearly the network is subdivided into 6 existing clusters and the nodes are correctly distributed over the sensing area. Also, there is no intersection between the different clusters. So this simulation of implementation of this algorithm clearly describes how the networks can be effectively partitioned into clusters much more than the previous algorithms. Now let's analyze the results in graphs for various algorithms that have been used in this. The first figure shows the number of nodes that are alive over time for the particular different 4 compared protocols. As you can clearly see from the graph, KSCA-WSN algorithm or our algorithm performs much better than all the previous 3 algorithms. It shows a significant improvement for this approach in terms of the number of periods relating to FND. In this method, the FND occurs at a period of 520 while it occurs at 378 period for spectral classification based near optimal clustering and 21 periods for LECHC clustering and 74 for DECSA protocols. So this shows that our particular algorithm has a much better performance in terms of FND also. Now let's talk about the second graph that shows about the evolution of remaining energy in the network when the transmission rounds are taken into account. This graph you can see that the network remaining energy decreases much more rapidly in spectral classification based near optimal clustering, the LECH and the DESA protocols than in KSCA-WSN algorithm. So our particular algorithm KSCA-WSN performs much better because here the network remaining energy decreases much slightly or residually as compared to all the 3 other protocols or algorithms where the remaining energy decreases much more sharply or rapidly. Let's now compare statistically the various performances of our particular algorithm with other 3 algorithms. This figure shows the impact of the node density n on the performances of the various compared algorithms. For different values of n from 100 to 200, 300 and 400, we can clearly see in all the different values of the number of nodes, KSCA algorithm or our particular algorithm performs much better improvement in performance as compared to all other algorithms. It follows that even if the node density increases, the new approach still gives best results compared to the other ones. This next graph discusses the impact of initial energy quantity on performances of the 4 compared algorithms. Also from the graph, it is clearly visible that this proposed algorithm has much more important improvements as compared to the other 4 algorithms. It gives that FND round depending on the quantity of node energy that is initial in accounts. So once more, it shows that for different values of the energy, this new approach presents a significant improvement compared to all the other algorithms. Finally, let's draw some conclusions from all the various simulations that we have. We can thus conclude from the simulations in the graph that KSCA algorithm provides a significant performance improvement in terms of energy as well as lifetime gains compared to the spectral classification based on near optimal clustering, the ADCH centralized algorithm, and the DECSA protocols. The best results for KSCA-WSN approach can be explained by 3 points. The first point is that this proposal starts by selecting the clusters or the similarity nodes based before the election of the cluster heads. The second is the approach considers the WSN nodes' residual energies when electing the cluster heads, and a cluster head is elected at any position of the wireless sensor networks. Based on 3 important factors, this algorithm performs much better than the other existing algorithms. Finally, let's summarize the entire presentation as in this entire presentation and project had effectively performed and studied the usefulness of employing spectral clustering as well as residual energy concepts in wireless sensor networks domain. As expressed earlier, a thorough analysis of the simple spectral clustering concepts together with proper understanding of its application to graph partitioning domain using ratio cut and normalized cut algorithms were initially performed, and then finally we moved forward to implementing spectral clustering together with residual energy concepts in wireless sensor networks area. In this algorithm that was performed with particular simulation results and observations, we can veritably conclude that the aforementioned new approach provides a much better overall energy distribution and increases the network's longevity multiple times. In future, more research is necessary to improve clustering as well as selection of this cluster head process. There has to be much more research in this area. These are some of the references that have been used in this project. Finally, thank you and have a nice day ahead.